last time, where we covered the basics of graph algorithms, which included BFS, DFS, and Dijkstra. Okay, cool. Thanks, Avigna. So today we'll be going over slightly more interesting graph topics, which will be topological sort, Bellman-Ford, and Floyd-Warshall. These are extremely useful algorithms in most comparative programming problems, and most of graph algorithms covers these topics, especially to start off. So then let me share my screen. So I hope that's visible. Yeah. So let's start off with topological sort. So to cover topological sort, I'll begin with something called directed acyclic graphs. So last time we covered these two words, which are special cases of graphs. So what we did was that directed graphs are graphs where A vertex to B vertex does not imply that there is an edge from B vertex to A vertex. Basically, the direction matters. So if we consider the example of cities, it would mean that if you can go from city A to B, it does not necessarily imply you can go from B to A, similar to a one way. And we also covered what cycles were in graphs. The simple definition of cycle, which we covered, was that if you have some path of edges through the graph, and you end up revisiting the same and you end up visiting the same vertex with distinct edges, then this is called a cycle. So now the types of graphs which we are covering are called directed acyclic graphs. So I'm sure that everyone, just from the name, is able to tell what kinds of graphs these are. They would be directed, i.e. for all a comma b, which are in vertices, if a to b belongs to E, then a comma b is directed. This may seem like a lot of notation, but this just means for every. This, if you recall, is the set of vertices. This is the set of edges, and this is just how we denote an edge. So I hope the definition of a DAG or directed acyclic graph is clear. If it's not, you can just feel free to unmute and ask. Okay, cool. I see a lot of thumbs up. So then let's just dive right into it. Topological sort. So the word sort, when we use the word sort, we are trying to say that there is some sort of order amongst the set of elements. Well, when you're trying to sort a graph, what would you try to sort? If you recall, a graph is just made up of two sets, one which are the vertices and one which are the edges. So what you try to do is to find some ordering of the vertices such that it is quote unquote sorted. And that word sorted is what we will define now. So the objective of topological sort or top sort is that you're able to place all the vertices in some kind of path like this. So maybe I'll just move to the next slide. Yeah. If this is the graph that we had, the first question I would ask is this a DAG? Is this a directed acyclic graph? You can answer in the chat or just unmute and answer. Yeah, I'm getting thumbs up. I'm going to assume that means yes. Yes, it is a DAG. Is CDE not a cycle? Is this not a cycle? Yeah. It is indeed not a cycle because if you see, if it was a cycle, it would be something like this. But that is not the case. It's just that you have C to D, C to E, and D to E. You can't take a loop of these three C, D, E such that you start and end at the same vertex. So indeed, this is a DAG. Very nice. What we said is that topological sort is present for DAGs. So we do have a DAG. So what we would try to do is we try to arrange these vertices A, B, C, D, E. Maybe I'll just put them like this. But what we are trying to do is to ensure that there are no inversions. What an inversion means is that if there is an edge from A to B, then I definitely cannot have B before A in my ordering. Because I'll give an example of where we use topological sort to explain this. So suppose you're in a course in some college, and these are 5 courses that you must take to finish your semester. But some courses are prerequisites of the other. Say C is a prerequisite of D. And what we can do is we can mark this as a directed edge from C to D. And if you're considering the topological ordering, then obviously you cannot complete D before C. This is not possible. So it would have to be C and then D. So what we're trying to ensure is to convert this graph into an ordering such that if you have a directed edge from a vertex to another, the one which is from which the edge is originating is on the left. So a simple way to think of this is to order the vertices from left to right. This is not a precise definition, but conceptually, I hope it's clear what I'm trying to say from left to right. Okay, cool. So can someone give me a topological ordering? Okay, so let me define one more thing. In a topological ordering, all the vertices have to be there, and all the edges which are in the original graph must be present in the ordering. So can someone give me an example of, wait, first of all, does there exist a topological ordering for this graph? And if so, what is it? I see an answer. A, B, C, D, E. Okay. Quite a lot of you are saying A, B, C, D, E. Is it A, B, C, D, E because that's the alphabetical order in which they're present? I'm going to assume that. So maybe if I add another F, it would come here, right? If there's another vertex F and I have something like F to A, then this would be my topological ordering. Am I right? No? Okay. F before A. Interesting. Yeah. It is F before A. And the reason it is F before A is that that's the only way, like if we come back to the original example, F is a prerequisite of A, so there is no way I can be doing F after A. So as people are saying, it would be F, A, B, C, D, E. But let me just quickly explain why it is A, B, C, D, E. Yeah, so in the original graph, if you look at it, you have A to B. Then you have, okay, this was E. I think it got removed, my bad. Yeah, this was E. Now, if you look at it, you have A to B, you have A to E, you have D to E, you have B to C, and you have C to D. So another way of writing this would simply be A to B to C to D to E, and then you add these vertices, these edges, my bad. So does everyone see why this is indeed a valid topological ordering? There is a C to E edge as well. Right. C to E is also an edge. That is a good point. So C to E is also an edge, but the point here is that you have no quote unquote inversions. There are no two vertices which are in the wrong order. So I hope this explains what the problem we are trying to solve is. Is that clear? Okay. Yeah. Now I'll be explaining what I had written here, maybe on another page. Okay, I'll do it here because I have a graph run on the next page. Okay, so I will erase this. So last time we covered what the concept of a degree was. So the degree if someone does not know, is just the number of edges originating from a vertex here V. So I've underlined the word originating because it is slightly ambiguous. Because if I have an undirected graph, what exactly does originate mean? Because the term originate usually refers to direction. I'm coming from here, going there. So in that case, we just, for undirected graphs, we just say all the edges because there is no concept of direction at all. But for directed edges, this definition is actually wrong because you can have something like this, and then you can have something like this, and the degree of A would be 2. To solve that problem, we come up with two new terms, in degree and out degree. Just from the basis of the words, can someone tell me how you would define in degree and out degree? You can unmute or write it in the chat, your choice. In degree is the number of edges directed towards A. Okay, I see what you're saying, but does someone have something more precise? This is not wrong. Yeah, in degree directed towards A. Yeah, that's okay. All of these answers are correct. But what I was looking forward to, yeah, it's been answered. Incoming, outgoing, directed towards, directed away from. These are all exactly correct words because what you are saying is that if you have A, this would be an out edge because you're going away from it. And then if you had E to A, this would be an in edge, or it just contributes towards out degree and in degree respectively. So in degree of A equals number of edges such that A is second. Because if you remember, we defined E equals UV as an edge from U to V. So here V would have its in degree increased and U would have its out degree increased. Does in degree and out degree make sense to everyone? It's just plainly speaking, number of edges coming into me and going away from me. And note this concept is useful only in the cases of directed graphs. So, okay, as we already covered, this was the resultant graph for, oh, I think I must C to E here as well. This was the resultant graph for topologically sorting G. So, yeah, I will now be defining two new terms, which are source and sink. So, what do you think source sounds like? Source sounds like something which would have a lot of edges coming out of it. What does sink sound like? Have a lot of edges coming into it. Now that we've defined in degree and out degree, does someone want to give me a definition of source and sink in terms of in degree and out degree? Exactly. Source means that in degree is 0. So the source means that in degree is 0. This means that the out degree is 0. I hope that's clear from the example. If you had something like this, then it is a source and this is a sink. Note, if I had something like this, then this is no longer a source. If I have something like this is no longer a sink. So hopefully source and sink make sense. Does that mean that there can be multiple sources in a directed acyclic graph? That's a good question. We will be coming to it. We will be coming to it. That's a good question. Well, now that we've learned what source is, sink is, I don't understand in and out degree. Okay, sure. Uh, okay, so if I have A to B, let's see, I have some B, going to be this is slightly a bigger graph than I was thinking about originally, but let's think about A. How many edges does A have incident on it? There is A to B and there is D to A. So from this we can say that the out degree of A is just 1 because there is only one edge going out of it from A to B. If you had A to C as well, then this would be 2. And n degree is 1 because you have D to A. If you had E to A as well, then it would be 2. So in degree is just number of edges coming into me. Out degree is number of edges which are going away from me. Does that make sense? Awesome. Okay, so does someone have any propositions about DAGs, considering sources and sinks specifically? Interesting. So let me write down the first one. At least one source, at least one sink. Any other okay, a lot of agreements with this. Okay. So I'll assume that this intuitively makes sense to everyone, but it doesn't make intuitive sense to me. So does anyone have a proof for this claim that every DAG has at least one source and at least one sink? Or okay, there's another claim. At least one source or one sink. That's a different claim we have. Okay, so the proof that Harleen seems to be giving is that if this is not the case, cycles will be formed. Interesting. Interesting. Is everyone
So
satisfied with the proof? Yeah, Nand, go on. Go on. Yeah, I think you answered.
I'm not satisfied with the proof, mainly because you can have graphs with cycles which have sources and sinks, but also yeah.
Yeah.
So what you want to do is you want to consider a sort of topological sort, or the sorting that we defined earlier, at least. Okay, and my claim is that the leftmost element is always a source, like the one that we defined lesser than all of the other elements is always a source, and the rightmost, the one we defined greater than all of the previous elements, is always a sink. This is because if it had an edge to any of the prior elements, then you would have that, you could arrange that.
Yeah, that's perfect. I'll just explain the exact same proof in a slightly different manner, but the idea is exactly correct. So what I will say is, since we've just talked about topological sort, your idea works perfectly, but let me say, let us consider a maximal path P in G. The way I would define a maximal path is that it just is not a part of a path which is larger than itself. That would be a very basic definition of what a maximal path is. And then exactly what Nand said is what we will follow. Let this be U and let this be V. His claim is that U is always a source and that V is always a sink. And his argument is that, assume for contradiction, that you had some U dash here, which has an edge to U. This immediately breaks the claim that P is maximal. In the same way, if you had a V dash here, that breaks the claim that it's maximal. So these cannot exist. So the only other place in which an edge from here could exist is on the path itself. But this is also a problem. Can someone tell me why? Either of this is also a problem.
It forms cycles.
Exactly. We have a DAG, that means it's acyclic, and this is a cycle, this is a cycle. So now is everyone convinced that U is a source and V is a sink and they must exist in a DAG. I hope now everyone is convinced with this. Yeah, getting thumbs up. Cool. So, this doesn't this give us a rather straightforward way to find a topological sort? Does someone see this? Okay, find U and start from there. Interesting. Okay. So the first part is correct. Let me erase this part. Yeah. The first step would be find U. And note that what he says is correct. Your topological order will begin from U because it's a source. But okay, let me throw something at you. Let G dash equal to G minus U. Let me remove U and its incident edges from G. Is G dash a DAG? That's the first question. Is G dash a DAG? Okay, that's a question. Okay. Okay. I will get to that in a minute. But let's define a DAG to just be directed and acyclic for this moment. Does this graph follow that? Is it still directed and acyclic? Yes, exactly. We will get to the connected, disconnected part later. But it's still a DAG, right? And a DAG will have a source and a sink. We proved that already. So G dash will also have a source. A G dash will also, yeah, okay. G dash will also have a source. Doesn't this give me a topological ordering? Here is my algorithm. Find U, find a source. G dash is equal to G minus the source. Repeat. Yeah, that's the algorithm. Won't this work? Yeah, it works. Does anyone see a problem with this? Yeah, so a problem two people pointed out is that if it's disconnected, we wouldn't want to stop at V. You'd instead want to stop when there are no vertices left. And there's a counter response that you can look at all components. Okay, I'll just answer that question. We are considering graphs which have edges because if you don't have edges, you can just return the vertex set, and any permutation of that will be a topological. It'll be a topological sort, right? Because they're like no dependencies. This is your graph, then you can just permute it in any order, and that would be a topological sort. Yeah, go on. Yeah, yeah, go on. Nant, you're unmuted.
Oh, sorry. I meant to say yeah, I wanted to say that looking at all components accounts for the no edges thing.
Okay. Well, yeah, there's absolutely nothing wrong with this algorithm, but there is a practical problem. So, can anyone give me a recurrence relation for the time complexity of this? Or T of n is the time taken if you have n vertices. What would be a recurrence relation for the time complexity?
How are we computing, what do you say, vertices with in degree equals 0? Are we like scanning through them every single turn, or are we just doing it delete edge wise?
So, okay, your question is how do we store the in degree of all the vertices, right? That's the question.
So if you're scanning every single time, then it becomes like n square.
Exactly. So you've answered the question as well, and that was the question I was going to pose. So the naive implementation would be giving you this. T of n would be T of n minus 1 plus n, because I'm pretty sure this is obvious for everyone, because the T of n minus 1 comes up because you're removing one node, and the O of n computation is every single time. And this, as Nand said, is O of n squared. Scan once, and then after every deletion, just update values. Okay, yeah, I'll get to how we can improve this. But does this make sense? Why this, in its naive implementation, is not very good? It's n squared. Does that make sense? Awesome. Okay, so I was going to say, can we move to Flood Varshal? But of course, you can't, because this is not the best possible implementation. So, as the others were saying, what you can do is, suppose you want to save on this time, where every single time you're scanning to find the source. Can we use in degree and out degree? Turns out we can. If you delete a node, what happens? If you delete a node, remove, say, you. What happens is that every edge, every vertex which u was connected to would lose its dash degree by 1. Would this be in degree or out degree? I am getting different answers. Yeah, in degree is the correct answer. And yeah, in degree is the correct answer, assuming that u was source. Sure. In degree by 1 is the correct answer, because you have an edge like this, u to v, and this edge is getting removed. So it was coming into me, right? It's not going out of me. So that's why in degree would become lesser. So, does anyone see an algorithm for topological sort from this? I'm pretty sure most of you do almost instantly. What people are saying is scan and store. Now, this is quite a useful trick in graphs in general. Instead of computing something on every single iteration or every single time we need to perform something, if we can store it once and then on each operation just modify what we stored, then that saves a lot of time. This trick is called pre-computation. Just, I mean, if anyone is curious, it's called pre-computation. This trick is called pre-computation, and this is the algorithm which everyone was suggesting. So I've written it out. There's some notation here, so I'll go through it once, but I'll give everyone a minute to just read it. So now, does this make sense? Let S be the set of all sources in G. What problem does this solve? Last time, last time, when we had the previous algorithm, some questions which were brought up were, what if it disconnects the DAG? Exactly, it solves disconnectedness. So now, if we have the set of all sources, then this would be similar to, I'm going to draw a comparison here. In DFS, what we did was, if we had our DFS running once and it did not reach all the vertices, we just ran DFS again from the next vertex. That next vertex is similar or analogous to a source. It's not a source because it's not a DAG, so you can't bring that into the picture, but the idea is kind of similar. So, okay, that was a bad erase. That's the problem this solves. I hope that why we are considering letting S be the set of all sources helps. Now, while S is not empty, What this does is it ensures that you have at least one source remaining. So you can take any source, add it to your L. L is the answer, by the way. L is the topological sort output. And you remove it from S. So I'm pretty sure this much makes sense to everyone. Then what this line is saying is for all V belonging to N of U. This just means for every vertex in the neighborhood of U. That means that if I had an edge from U to L or U to M or U to N or any of these, then L, M, N, all of these would be in the neighborhood of U. And they would be the edges that we consider here. Their n degree becomes one less. And here, this is the crucial step. If the n degree becomes 0, add it to your set of sources. And then output L. Now, if this algorithm makes sense to everyone, then I have a question. Does it make sense to everyone? Neighbor both, sorry, Nehal, what do you mean? Can you explain it again?
Does that mean that in the neighborhood both in degrees and out degrees would be considered?
Okay, I see your question. So you're saying if you have something like this, U to V, and then you have N to U, right? You're saying you have something like this. Well, in this
Yes.
case, we're only considering the neighbors. That means from U, where can I reach? From U, I can't reach N. I can only reach V and M. So those are the two I would consider. In an undirected graph, yes, N, V, and M, all three of these would be part of the neighborhood. But in this scenario, just V and M. That's a good question. I hope that question is answered. Yeah, and I'll get to the second question, which was in the chat. What if we try to run this algorithm on a directed graph which contains cycles? So I've been saying many times, DAG, 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 DAG. The directed part probably makes sense to everyone because that's the whole point of having a prerequisite. But why does it have to be acyclic? Does someone else want to answer this? Why do I need the graph to be acyclic? Infinite loop, okay. Any other answers? Does someone want to unmute and explain, perhaps? Okay. So, if you had a situation like this, okay, wait. If you have a situation, let me find some empty space. Yeah, if you have a situation where you have A to B to C back to A, you might not have a source in the cyclic graph. That's a very good point. You may not have, wait, actually, I have to think about it. You may not have a source in a cyclic graph. Exactly. That's a very good point. Like, this is an example for that. There's no source in this graph, first of all, because each edge has in degree equal to 1 and out degree equal to 1. So that's one valid point. And the second thing is that if you try to find an ordering of this, you would go, okay, A to B, because that's a prerequisite, B to C, because that's also a prerequisite, but C has to be before A. So it is just not possible to have this for a cyclic graph. Yeah. And the other point which was brought up is that you may not have a source in a cyclic graph. That's also a very valid point. So this algorithm may not run itself. Well, I have a question now. If this graph algorithm makes sense to everyone, can someone prove that this algorithm will actually terminate? Will this loop ever end? And will I ever reach this line at all? Can someone give me a proof for why I will actually get an output of a topological ordering? In a DAG, the number of vertices always reduce after each iteration. Okay, yeah. We only visit a node once. I'm not quite sure what you mean by that. I think I get what you're saying, but maybe you want to say it in a different way. Removing a source creates. Okay. So I think we've got the correct idea. The idea is what Nand and Nishant have said. In a DAG, the number of vertices will always reduce by one. What this means is that what we are doing is we are removing a vertex here. The only case where we won't reach here is that if this didn't happen. And if this didn't happen, we would come here and we would have an output. Now, what Nishant is saying is that if you remove a source, if you remove a source, then you must have at least one new source unless the graph is over. So what he's actually trying to say here is either this line is true or false. We know that. If this is true, you must have a source which gets removed, which means that one vertex has been reduced. Or we come here. So both these arguments are on the critical point that at each iteration, number of vertices go down by one. And in the end, if you have no vertices, then S is empty and the algorithm does not satisfy this loop and thus comes here. So after all of this lot of stuff written here, does topological sort make sense? If there are any questions, can we use topological sort? I mean, if you consider the fact that topological sort will give you, see, you can't run topological sort on a directed graph. It will not give you a topological ordering because if we come back to this example, this does not have a topological ordering. You will, so if you're saying that the fact that I don't have a topological ordering signifies it's a cycle, then sure. But there are much easier ways to detect cycles in directed graph, and the way to do it is just DFS actually. But I mean, hypothetically, what you're saying does kind of make sense, but it's a bit of an overkill. How do we construct the set S? That's a good question. So, what does S consist of? S consists of all vertices which are sources. And what is a source? If you go back to the definition, a source is something which has in degree zero. So, if you just run through the adjacency list of the graph and check the in degree of each vertex, in O of n time, you would be able to compute the set S. Does that make sense? Okay, I'm going to give everyone a minute now to think about the runtime of this algorithm. Just, yeah. Any claim for what the runtime is should at least have a one-line description of why you think that's the runtime, because otherwise guessing n plus m is a very nice thing for most graph algorithms, because we've seen 3 graph algorithms so far. 2 of them are O of n plus m. So why don't I just guess n plus m? So instead of that, maybe you can give an explanation of why you think it's n plus m. A basic, just a one-line argument. You can unmute if you want, or you can write in the chat. Because we come across, okay. Can you explain it to me through the algorithm, maybe? Oh, interesting. O of n squared. Now that's a different argument. Okay, we are getting a lot of different answers here. Okay, I'm really interested. Bhairav, why do you think it's O of n squared?
Because in this implementation, we are taking O of n time to get the set of all sources. Since we're just iterating through all the vertices and checking whether they're a source.
Okay, so maybe this line is O of n, but then why is it O of n squared in general?
No, because oh wait, I thought we were recalculating the set of all sources each time.
Yeah, so that's a good point. That's the question we solved by doing this. Since we are doing this, we are not recalculating the set of sources every time. So do you get why it's not n squared?
Yes.
Okay, so what do you think the answer is? Anyone else? I've got n plus m, n log n plus e, a lot of different plus m, a lot of different answers. Maybe we can just analyze this. Okay, no, O of n plus m makes sense. Okay, so the general consensus does seem to be O of n. And I'll give a basic justification for why. Maybe I'll open a new page. So, yeah, okay, that is. So O of n was my pre-computation. And then for each vertex, I'm going to at most out degree of u. And then the sum of this is 2m, I think. So you have O of n plus 2m, and you take big O of this. And that's just asymptotically O of n plus m. Does that make sense to everybody? This is 2m, right? Yeah, it's O of 2m. So even if it's O of m, I'm fine. So asymptotically, the constant is just dropped. So you have O of n plus m. So does that argument for the runtime make sense? So this is actually a very valuable thing to think of. That if I have any directed acyclic graph, any DAG, topological sort is basically free because it's 2m, because I think there are at most 2 times the number of edges. Oh, okay, never mind. I got confused. 2m is for a different scenario. Okay, never mind. It's not 2m. You're right. We go over each edge once. It's just m. Even then, asymptotically, the answer would be correct, which is why I was not that worried. But you're right. It's O of n plus m, just not 2m required. So it's just O of n plus m. But okay, I'll come back to this. Topological sort is basically free. Can someone justify this statement or disagree with it if you want to? Yeah, you can define the term free. I'm saying it's free. What do you think free means? Free means it's not going to hurt me at all if I use it. It's no cost. So what do you think? Why am I saying this? Why do you think I'm saying this? Okay. So what Nishant is saying is that it's the same complexity as BFS and DFS. And from that, what he's trying to say is that if you have a graph problem and you want to run some algorithm on it, the simplest algorithms we know are O of n plus m. So why don't I just run topological sort on it? And it just, for me, if I look at a graph and I look at its topological ordering, the topological ordering is much more pleasing because it looks a lot more ordered. So if it was just O of n plus m, and then I run BFS on it, it's not going to cost me anything asymptotically. Now, what Avigna is saying, what if I run topological sort n times? Then it becomes O of n and O of n plus m, which becomes O of n squared. But my question to you is, why would you ever want to run topological sort n times? Topological sort, if you run it once, you're going to get the ordering. Why would you need to run it more than n times, more than one times? Can you repeat the last part? Okay. So I'm assuming that's Avigna's question. So what? Okay, I can add another page. Wow, I did not know that. That helps a lot. So what you're saying is that BFS is O of n plus m. DFS is O of n plus m. Now, top sort is also O of n plus, is also O of n plus m. So if I have some question where I'm going to run BFS and DFS on the graph, I can just run topological sort on it for something which is basically not going to cost me anything or free. Okay, and now something which you can actually afford to run n times. Yeah. So the point is that if you have to run topological sort once, then it's basically free. It's not going to cost you anything. But if you have to run it, say, n times for n queries, where suppose you maybe remove an edge, add an edge, some different form of the graph, then it is not free because it becomes O of n times n plus m, which is asymptotically O of n squared, which is just bad. But in the case where you have to run it once and you want a topological ordering, it's a very nice algorithm to run on a directed acyclic graph. So we covered two algorithms of topological sort, but one of them is just a betterment of the first. The first one was this algorithm. It's just this algorithm where I don't do this. And as Bhairav pointed out, that's O of n squared. I think it was pointed out before as well, because we did the recurrence relation and all of that. Well, I'm going to give one last algorithm for topological sort, and this is a very quick one. And I'm going to give a hint for that. If you see O of n plus m, you'd say BFS or DFS. Well, now you can say top sort as well. Does anyone think there's a relation between top sort and BFS, DFS? Maybe I can use one of those for topological sort. Does anyone see a way I can do that? Okay, so I'll ask you guys a question here. This is a very nice thing to find out on your own. Do you want like just take a graph, do BFS, DFS on it, and find the topological ordering, and then you just see what you get and try to find a pattern? Do you want me to quote unquote spoil it? It's a nice thing to find out on your own. I can say it. So you guys tell me. Do you want me to tell it? It's your choice. DFS does have an interesting property you can exploit. That's right. Diverse graph, DFS to sync, remove each. Okay, I'm just thinking about this. Just give me a second. This, yeah, exactly. It doesn't work for multiple sources. But it's an interesting idea. I've seen reverse edges a couple of times. What reversing the edges will basically do is switch the source and sync. But that doesn't seem to give me that much, does it? So, okay. I'm planning to tell the algorithm. If people object, just tell me now. Otherwise, I'm going to spoil the thing. So it's your guys' choice. What do you mean by stack property? Yeah, I will go over that. That's what I'm saying. Do you want me to say it, or do you want to try and find it out on your own? Okay, I don't think anyone has an objection, so I'm going to go over it. So when we do DFS on a graph, I think this is what stack property is referring to. I've just not heard the word being used that way, but I think it's the same. Yes, you will. When you do DFS on a graph, what we can say is have a time counter. So when I am doing DFS on the graph, let the time at which I start the DFS be 1, and at each quote unquote operation or step, I increment the time by 1. So when I go from A to B, let us say this is the reaching time, or the time where I first saw the vertex, the encounter time. I'm trying to remember the exact term which is used. Okay, I don't remember the term which is used, but I think reaching time is fairly discovery time. Yeah, discovery time. Yeah, I just blanked for a second. So we call the time discovery time, and that's the point where you first find the vertex. So for A, it's 1. For B, it's going to be 2. Then for C, it's going to be 3. And for D, it's going to be 4. And when you have discovery time, automatically you have something called finish time. And finish time would just be when the vertex is completely explored, when you have no other connections or edges you can derive from that vertex. So D will be 4, 4, C will be 3, 5. Exactly. So here, if I add, it's called finish time. Yeah. This will be 4. Sorry, this will be 4. Yes. This will be 5. This will be 6. And this will be 7. Now, yeah, thank you so much for that honor. So if I wanted to top sort on G, can someone tell me what the topological sort is? This is quite an obvious one, so you know what? I'm just going to write it. It's A to B to C to D. Does anyone see a pattern? Surely someone sees a pattern. Ooh, descending order. No comments. Starting time in ascending order. Of course, someone had to say that. Starting time in ascending order. So, okay. Starting time in ascending order clearly will not always work, which I think is like, I can leave it as an exercise for you to prove. But this works. Descending order of finish time. The descending order of finish time does work. And yeah, you can just have 2 branches. And if you have something like this, it will not work. So if you consider this, the decreasing order of their finish times, that is actually just going to be the topological sort of the graph. So the algorithm is quite straightforward. You run DFS on G, sort the vertices in the decreasing order of their finish time, and that is your topological sort. Yes. So this may not intuitively make sense, but let me try and give a brief example of why. If you consider the finish time of I and J, if I finishes first, you can find some relation of it with G. I don't want to go through the entire proof because it requires some properties about DFS like parenthesis and white path and stuff like that. But I will go over the runtime. So does anyone want to quickly tell me what the runtime of this is? I think I had some glitch. Okay, yeah. I am back. Okay, I see an option immediately, O of n plus m. Okay, interesting. Totally not seen this word. Okay, O of n plus m. Interesting. Can I do sorting linearly? Okay, I can't see the chat from before. So if there was something else other than n plus m, could you send it again? I am going to leave this as an exercise, and please, someone, the first person who can prove, send me the correct uh, runtime with proof. Good job. So yeah, I am leaving you in suspense with the runtime of this. But just I'll give one hint. We already saw one algorithm of topological sort, which was n plus m. Would it be worse? Would it be better? Would it be the same? So that covers topological sort, and I hope everyone understood how unique topological sort n log n. Okay, let's add n log n. How unique this algorithm is because it allows us to, in linear time, find an ordering of a graph. Because linear time is the amount of time you need to quote unquote read or go through the entire graph. And if you're able to order it in that much time, it seems like a steal. So there is this problem, CSES course schedules. I will just share my screen and show that problem. It should be a straightforward solve now that we have gone over topological sort. Let me share my screen. Okay. So this problem is the one which we are kind of originally talking about, where you have n courses and you have a prerequisite. Your task is to find an order in which you can complete these courses. So I feel like this one is now just a straightforward application of topological sort, right? I hope everyone sees that. Okay, I'm just going to assume that everyone understood how you can do this in with topological sort because it's quite it's basically just the algorithm which we covered. Yeah. So I'm going to go over one last thing about topological sort, and I'm going to do it a bit quickly because we're running out of time. So, and that's going to be a DP on DAGs. So one of the main functions about directed acyclic graphs is how easily you can do. Oh wait, I'm not sharing my screen. Okay, let me share my screen again. Zoom. Just a second. Okay, so DP on DAGs. So we can use dynamic programming on DAGs in quite a few ways. So once you have a DAG, you run topological sort on. On the topologically sorted graph, you can do many functions using DP. One is you can count the number of paths from say A to B. You can find the shortest path. You can find the longest path. I'm just going to give an intro to how DP on DAGs would work, and then we can move on to the next algorithm. So suppose you have this graph. I hope everyone can see that this is the DAG. Then if you want to go from A to F, you can see that there are many ways to do this. You can go like, I think I've written the paths here. I hope I've not made a mistake. A, B, C, F, A, E, C, F. Oh, sorry, A, D, E, C, F, and A, D, E, B, C, F. There are three ways to do this. But I can also find this out for any graph, however dense, however sparse, using dp. So let dp of x be the number of paths from, say, vertex A to x. A here is your starting vertex, and this is your ending vertex. So dp of A is just 1, and this is what we assume it to be as the base case of our recursion. So the number of paths from yourself to yourself is 1. You just, yeah, okay, it's 1. So let A have k neighbors, and let them be A1, A2, dot, 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 up to AK. So does someone see why this holds? Does everyone see why this holds at least? Yeah, I think there was a mistake. It should not be I, it should be AI. But yeah, does everyone see why this holds? Because the number of ways on which I can reach from A to X is the same from like A1 to X plus 1, which is this value itself. So I hope this makes sense. And now, since we have a DAG, this is the same as calculating the values in order. Because as you're moving from left to right, you would move from A to the layer containing A1 till AK, and then you'd move on until you reach X. So this is a cool property of DAGs, that you can traverse and find values in the order of the topological ordering itself. Does that make sense?
Yes.
Okay, cool. So with that, topological sort comes to an end. And there are two more algorithms which I'll quickly cover, quite quickly, because we do have a quite sharp ending time. And the two algorithms, okay, I think there's a glitch. Yeah. The two algorithms which we'll be covering are Floyd-Warshall and Bellman-Ford. So I will start with Floyd-Warshall. Okay, just give me a second. So many times when we talk about graphs, the main reason we use this data structure is to find shortest paths. It is one of the main utilizations of the data structure. So Floyd-Warshall also gives us a method to find the shortest path. However, it has one key and I'd say differentiating feature from other algorithms like BFS and DFS. What BFS and DFS do is that they find shortest paths from a specific node to another specific node, or from a node to all nodes. What Floyd-Warshall does is, for all pairs of vertices, so like if you have any two vertices U and V, it'll find the shortest path between them. So if I have these 5 vertices, it'll find me the shortest path from 1 to 2, 1 to 3, 1 to 4, 1 to 5, 2 to 3, and so on. Every possible pair of two vertices will have the shortest path between them found by Floyd-Warshall. Is the objective of Floyd-Warshall clear to everyone? What it does is that it finds the distance between all possible nodes. Explain again. Okay. So this is not what Floyd-Warshall does. It's just what Floyd-Warshall gives you in the end. If you have any graph, say this is the graph, it will give me the shortest distance between every pair of two nodes, from 3 to 4, 3 to 5, and so on. Does that make sense? Okay. Yeah.
Yes.
So how Floyd-Warshall works is, I've given an example here. What it gives you is a 2D array which stores distances. What it does in the beginning is, for all pairs of vertices which do not have an edge between them, let the distance be infinity. So if you see here, the 3 to 1 does not have an edge between it. So 3 comma 1 and 1 comma 3 are both infinity, because we're dealing with an undirected graph here. The same way 4 comma 2 does not exist. Okay, so we can tell from here itself 2 comma 5 should not exist, and it doesn't. 2 comma 5 doesn't exist. Yeah, so I guess that part is clear. The second part is these green values and these purple values. I've divided it into blue, which means no edge. Green is all values on the diagonal. Diagonal values are of the form I comma I, 1 comma 1, 2 comma 1, 2 comma 2, 3 comma 3, and so on. So from yourself to yourself, your distance is 0 because you're at that point itself. So it's just 0. And then for everything in purple, it's all the edges which are actually present in the graph. So if you have 4 to 1, this edge is which we are talking about, it has this weight 9. So if you look at this value and look at this value, they both are 9. So this is the original distance array of Floyd-Warshall. Does the original array make sense? Awesome. So what Floyd-Warshall does is that it considers intermediary nodes. So the path Floyd-Warshall did not consider for 2 to 5 was that I can go from 2 to 1 and then from 1 to 5. So 1 is what we call an intermediary node. Okay, I'm not going to write it because there's no space. We call it an intermediary node. So what Floyd-Warshall does is that it considers every possible intermediary node, and for each of those intermediary nodes, it updates the distance array. So this is the next step where it took 1 as the intermediary node. And we saw that some values will now change. Right? Let me just draw out which values will change. So you can have 2 to 1 to 5. So now 2 to 5 has a distance of 6. So this value will change and this value will change. Similarly, I think there's one more path. Yeah, 2 to 1 to 4 is also a path. So now 2 to 4 will have its value changing, which means this value will change and this value will change to whatever the sum of the two was, which is 14. So those are all the paths which I can change having 1 as an intermediary node. Now what Floyd-Warshall does is that it says, okay, I'm done with 1 now. Let's move on to 2. If 2 is an intermediary node, what else is possible? 1 to 3 is possible with this method, or maybe, okay, what else is possible? Yeah, I think that's the only one possible. Oh, okay, 3 to 5 is also now possible because 1 is already an intermediary node. So you can go from 3 to 2 to 1 to 5. So those values will change. This value will change and it will become, this value will change, and 5 comma 3 will also change. So this process is what Floyd-Warshall keeps on doing, and every time it finds something which is better than its current value. So it just takes the min. If I'm at 10 right now and I find a path which can get me to another place in 8, then obviously I will change 10 to 8. But from 10, if I become 12, I'm not helping myself. I'm not finding the shortest path. So we just leave 10 as is if you have a value which is greater than that. If you have a lesser value, awesome, let's change it. So here is an implementation of Floyd-Warshall which has a mistake in it. This implementation has a mistake, and I want you to find the mistake for me. Dij is the distance from I to j, and n is the number of nodes. I think, yeah, this should be sufficient to find out the mistake. Why is there a second min? O of n cubed, okay. Sorry, how is O of n cubed? Like, that's the time complexity. We'll come to that later. But yeah, okay. Yeah. We've got a lot of people saying this. This min is not required. And that's right, because we only consider min when you're doing your final comparison. Is the value better than mine or not? We're not doing min in the actual computation. The actual computation would just be finding out the value. So if I remove this min, my answer would be min of, this min is the one I'm removing, not this, would be df I comma j comma df ik plus df ij plus d of kj. Does everyone agree with this? Okay, I'm still getting no. So people are saying there's still a mistake in this? Exactly. There is an extra dp of I comma j which is being added. This should not be added. And the reason that is that if you're considering your new value, the new value is formed because you have a new path. The new path does not have to take the value of the original path. The original path is one way to reach from I to j, and here you have a second way to reach from I to j. So this is not required. And as I think a lot of people said in the chat, the correct thing would be this min of dp of I comma j, the min of dij, and dik plus dkg. And that is how Floyd-Warshall works. So I hope Floyd-Warshall basically is clear, and we can answer that with what's the time complexity and what's the space complexity. Okay, I'm just going to go over it. It's O of n cubed and O of n squared. The reason for this is this. This is the reason for O of n cubed. Yeah, exactly. Someone has said that. That's absolutely correct. And the reason he's saying V is we define V as the number of vertices, which is the same as n. So that's the same idea. So the reason it's n cubed is that if you have, yeah, both answers are correct. You're going from k from 1 to n, I from 1 to n, and j from n to n, and these are nested. So you'd have n iterations, and for each of the n iterations, you'd have n squared iteration. So it comes out to being n cube iterations, due to which time complexity is n cubed, and the space complexity is n squared. Now I have a claim. Floyd-Warshall is nothing but useless. If I have an O of n cubed algorithm, how will this ever help me? We were having problems with an n squared algorithm. So what's wrong with how is n cubed ever going to help me? I see some no's. Can someone tell me when n cube will ever be useful? Yeah. So I think the answer is basically correct. First of all, yeah, that problem, okay, maybe you shouldn't spoil that problem. It's going to be a part of the problem set. So probably don't spoil that problem. Yeah, I don't know what that means. So the reason O of n cubed is actually still feasible is that in cases where n is small, when the number of vertices are small, O of n cubed is perfectly fine. And the other case in which Floyd-Warshall is extremely useful is where you have queries. If you need to find the distance between I and k the first time, and then L and M the next time, and then N and J the next time, you can't keep running BFS again and again and again and again, because then you would have something like O of n plus m times q. And if q becomes very large, q is the number of queries, then this algorithm is going to be like this or even worse. And the implementation of this is quite obvious. You just have 3 lines, which are your beginning part, the iteration of ki and j, and then you have the algorithm. And there's a setup, which is another couple of lines. So as people are saying, for subtasks, this is extremely useful. But there are cases where Floyd-Warshall can AC, but really the main utilization is for subtasks. So that covers topological sort and Floyd-Warshall. Floyd-Warshall does have a lot of uses in implicit graphs. In cases where the graph isn't exactly obvious how to create it, those questions will be in the subtask, in the problem set. And problem sets for BFS, DFS, and this combined will be sent out on SPOI. So let's go on to the third. Okay, so Ovian has sent a question where the AC solution uses Floyd-Warshall. So we can definitely, everyone can take a look at that. So yeah, we now move on to the third algorithm and the last algorithm, unfortunately, which we are going to be discussing today. And that is Bellman-Ford. Okay, so this is what I see here. The shortest path from a node to all other nodes. Isn't this something which we've already discussed many times? There's a catch. The first thing is that it's weighted. Well, that's still not a problem. I have Dijkstra. We covered Dijkstra last time. Why can't I just use Dijkstra? Now, I remember a lot of times when I was doing Dijkstra, people are saying, what if the edge weights are negative? What if the edge weights are negative? And what we said is that it's an assumption we make for Dijkstra to work that all edge weights have to be positive. Well, Bellman-Ford solves this problem. Just a second, there's a question in the chat. We're getting to that. Dijkstra fails in negative cycles. And I will explain that with an example, which is here. Yeah. If you have a graph like this, where these are your vertices, these are your edges, and these are your edge weights, you can see that 2 to 3 to 4 to 2 is a cycle. And if we add the weights, that's 2 minus 7 and 1, we get minus 4. This is a negative edge weight cycle. And for some reason, which we will come to later, Dijkstra fails for this. Dijkstra fails for negative edges, period. Bellman-Ford allows you to find such negative edge weighted cycles. Oh, by the way, just a theoretical point. You wrote that Dijkstra fails in negative cycles. The more, like the way we usually say it is, Dijkstra cannot handle negative edge weights itself. But yeah, that answer is not wrong. It's just, this is another way of saying it. So yeah, now let's go over what Bellman-Ford does exactly. Yeah. Okay. So what Bellman-Ford does is quite similar to Dijkstra. It maintains distances to nodes from the beginning or source node. It tries to maintain distances with all the nodes. And every time it finds something better, it just reduces. This is similar to all graph problems. But what Bellman-Ford does differently is its handling of negative edge weight cycles. So here is the implementation of Bellman-Ford, or at least the pseudocode. So let the source or the place from where I'm doing Bellman-Ford be X. So this is the number of iterations I'm going to be running. And this line, let's keep it as a question mark from now. For now, let's keep it as a question mark. But let's just look at this part. Distance of X is 0 because that's the place from which I am running my Bellman-Ford. And then for B, and let's just say you have, this is the way you store an edge, an edge from A to B with weight W. So then distance of B is going to be the minimum of the distance of B and the distance of A plus W. So whatever A was plus the weight W, because you're going from A to B, or whatever B has been stored as it is. This is how Bellman-Ford works. And what Bellman-Ford does is that on each iteration, it tries to reduce these distances. And the way we use Bellman-Ford is to run it n-1 times. In each iteration of Bellman-Ford, what it does is that some nodes will have its value of distances changed. This is because you found a more optimal path. Now comes the main part of Bellman-Ford. So this is how Bellman-Ford works in general. You run it n-1 times, and you can find the distance from a node to the other nodes. But that is something Dijkstra could do for me as well. The only exception being that negative edge weights were not allowed. What Bellman-Ford can specifically do is it can find negative edge weight cycles. It can find something like this for me. And the way it can be done is to run Bellman-Ford the nth time. Now, I'm going to tell this to you. Someone has...
What if, excuse me, I just want to say something.
Yes?
But what if there is a negative cycle in then Bellman-Ford should fail? Like, the every time would a value be updated, then there would be a cycle. Like if there was a negative cycle, then it would just continue going till it, because every time there is a value change because of the negative cycle.
Okay. So what you're trying to say is that if I have a graph with a negative edge weight cycle, Bellman-Ford will fail. So this depends on what you define fail to be. Because no, it won't fail. In n minus 1 iterations, it will be able to find the distance. Exactly. Bellman-Ford has a decided number of iterations. Very well said. So what that does is it is able to give you the answer of the distance of nodes from your source in n minus 1 iterations. There's no problem with that. The only thing is, if we want to find whether there is a negative edge weight cycle or not, then we run Bellman-Ford the nth time. And can someone tell me how I will check by using it the nth time? Yeah, you can feel free to unmute and just.
Okay, so then if anything changes, then it'll. Okay, yeah. Yes, if anything changes on the nth step, then it'll have a cycle of a negative edge weight sum.
Okay, and what is your reasoning for this?
Because then, if it has changed, then the part must go in a loop. Otherwise, it would end up going. It has to go back somewhere else by pigeonhole principle. So that means that if it's better now, then the loop would be negative edge weight cycle.
Yes, this answer is correct. And the basic gist you can get from this, he gave the proof as well, the sketch of the proof. But the basic gist of this is if change cycle exists, else doesn't. So that is basically what Bellman-Ford is. So we covered 3 algorithms today: topological sort, Floyd-Warshall, and Bellman-Ford. I'll give a brief summary of all of these, and then if you have any questions, then I can answer those. But for all people who've understood, the lecture is, yeah, okay, I'll just give a summary and then the lecture is over. So, topological sort, given a DAG, I can run topological sort on it and get an ordering from left to right without inversions. And I'm using the word inversions in the way we defined it earlier. Floyd-Warshall in O of n cubed, I can find shortest distance between every pair of 2 vertices. Bellman-Ford, shortest path from source to all nodes with negative edge weights allowed, extra can detect negative edge weight cycles. So those were 3 algorithms which we covered today: topological sort, Floyd-Warshall, and Bellman-Ford. I hope these 3 are clear to everyone. And yeah, the lecture is basically done now. If there are any questions, please feel free to ask me. For the problem set, they'll be out soon for all the topics we've covered about graphs so far. But till then, you can always feel free to do CSES and the other resources which were mentioned by Ovian in the SPOI resources link. So are there any questions, or otherwise I think we are done? Yeah, go on. Yeah. Yeah. This is an interesting question. Do you think we can give it as theory homework? I think. Yeah, sounds good. And also the other thing, the runtime of the second algorithm of top sort, the same thing for that. If anyone figures it out, you can just put it on SPOI with a ping, and yeah, yeah. Okay, then I guess that's the end of the lecture. So yeah, I hope everyone understood and learned a lot. And do keep doing graphs. It's a really amazing topic, and it's really fun as well. Yeah.
Thank you. Bye.